Hello friends, welcome to my channel. Let's have a look at problem 1697 together, checking existence of edge length limited path. So in this video, we're going to share a solution based on disjoint set data structure, also known as disjoint set forest or unified. So this problem is marked hard in Leetcode. However, if we analyze the logics in this problem carefully, we can come up with a very succinct solution. So the main task in this problem is for each of the given query, we check if the two nodes in the query is connected via a path and the edges on the path have length strictly less than the limit specified in the query. So that's the main requirement or statement for this problem. So here are some examples. So we're going to walk through one of them after we analyzing the problem. So let's look at the constraints about this problem. So the number of nodes can be up to 10 to the power 5. So this number is a decent large number. So when we devise a solution to this problem, we shall take time complexity into consideration. And notice that the edge list and queries are both length 3. So the edge list is a form like this. It contains u, v, dist. So dist is the direct distance of u and v. And in the query pq limit, so we require that the edges connecting p and q have length strictly less than this limit. So that's the constraints about this problem. So with that said, let's look at the method. So as we mentioned at the very beginning, so the method we are going to use is based on disjoint set forest. So the idea actually is very straightforward. So we are going to use the disjoint set to cluster nodes according to connectivity and allowed path limit specified in this problem logic. So two nodes in the same clusters are connected via a path. So this is the main idea. However, there's a key question. So how to do the clustering? So we shall not do a cluster using all edges for each path limit in the query. That's actually too time consuming. So what we shall do is to sort the queries according to the path limit from small to large, and sort the edge list from small to large according to the distance element. So in the process, we gain a lot of things. So what have we gained after sorting on them? So here is the understanding. For an edge u, v, this. So if this is less than the current limit, path limit we are examining, then this will less than the limits in the later queries. So in the process of looking at the queries linearly, so if we look at the whole process globally, so we do not need start over from beginning for a new query. So the result is the following. Overall, we just need to check the whole edge list once and only once for all the queries. So that's the key point for this problem, incorporating the main logic in the problem statement. So next, let's have a walkthrough for one example. So this is a slight variant of example 1. So we changed some of the orders because the edge list and queries are not sorted a priori according to our needs. So we are going to first sort the edge list according to the third components of its element. So after sort is like this. So we are sorting according to the this for edge list. And for the queries, we also sort according to the path limit, both from small to large. So after sort, we're getting something like this. This is the path limit, this is the two node, and this is the index, the query index. So we put this query index here for the purpose that we can later track and update the result at the correct place. So afterwards, we can initialize a variable called result, so whose final state is what we want to return. So initially, we set all the places to be false, and this length equals the query length. So for the first query, so we examine this one. So the path limit is 2, so no union operations happen. So the clusters are 3, so each node itself is a cluster. So node 0 and 1 are not connected via path, so result 0 remains false. So when we examine the second query, so the path limit is 5. So these 2 and 4 of distances are strictly less than 5, so we have union operations happen. For example, if we look at 0, 1, 2, then 0, 1 forms a cluster. When we look at 1, 2, then 2 should merge with 0, 1. So we have a cluster 0, 1, 2. Therefore, the nodes 0 and 2 are connected. So we reset the state for result 1 to be true. So the final return for this problem is false and true. So that's a full walkthrough for an example. So next, I think we are ready to look at the solution code for this problem. So first, I'm going to do some initialization. So here, I'm going to use a vanilla union just for convenience. So I'm going to initialize a parent dictionary, which will store the node and the parent relationships. So for I in range n. So this is the initialization. Now we're going to define the find and union method quickly. So define find I. So here I is a node. I is a node, or as for example 0, 1 up to say n-1 in this specific problem. So then we're going to check if I does not equal to its parents. Then we're going to set the parents of I to be that of the self-call parents I. So afterwards, we're going to return the parents I. So this is the find function. So there are a number of different formats of implementations. Actually, all are good to know. So next function we're going to implement is a union. So it accepts 2 arguments. Let's call it I1, I2. What we are going to do is that we check if I1 and I2 are in the same cluster. If not, we're going to merge them. So for this, let me first track the delegate or representative of I1 and I2. So find I1, find I2. So then we are going to check if they are the same or not. So if they are not the same, we are going to merge them. So it corresponds to reset the parents relationship. So let's set the parents of R2 to be R1. So you can do the reverse. It's still okay. So that's the implementation for the union. So I would say the find and the union is just a very short function here. So next we look at the main logic for this problem. First, I'm going to sort the edge list. So we are going to sort according to the this component. That is, the sort function is this x2. So here, let me make a remark. So we are sort by the this, right? Then we are going to sort the queries. Before we doing the actual sort, let me first make a new list so that we can find in the afterwards we can easily track the query index. So I'm going to do limit pq I. So for I pq limit in enumerate queries. Then we are going to sort this query according to the limit mainly. So if we do this sort, so the limit, the path limit is in ascending order now. So that's the preparations. And also we want to track the length of the edge list and also the queries. So let's call this n edges and n queries. This is the length of edge list. So this is the length of queries or queue. So let's write queries just for clarity, right? So with that said, we're ready to write the main logic and prepare the return. So let's initialize a result variable and set all the blobs to be false. The length will be the n queries. So that's the preparation or initialization for the final return. So now we are going to do the possible necessary unions. For that, let me first initialize a edge index to be 0. We're going to start from the first edge after sorting. Then we're going to look for each of the queries. So for path limit, PQ, and query IDX in Q. So here PQ are the two nodes for which we're going to check if they are connected. So the path limit is the requirement that for a path that connects PQ, all the edges should be strictly less than this path limit. So the query index is the position of the query in the original queries. So with that said, we're going to look the conditions. Basically, it's a while loop. While edge index is less than n edges. So we make sure that we are not auto bound. And also we need to check edge list, the edge index, the second component. So in other words, this component is less than the path limit. If this is the condition, then for the current query and for the current path limit, we can do the union operation for the two nodes in the edge list, edge IDX. So let's track the edge first. So the edge is nothing but edge list, so edge index, so the first two components. Then we're going to union these two nodes. So let's do the union. So let's do this edge. So this star edge corresponding to put the two nodes of edge into this union. So with that said, then we're going to see the next edge, allowed edge, I will see. So that way, after we exit this while loop, then for the current query, we finished all the necessary union operations. So this is the state that's suited for the current query with the given path limit. Then we are going to check if PQ are connected. In other words, if they are in the same cluster. So basically, we are going to set the corresponding result. How do we find the which position we should adjust? That is the query index, right? So then we're going to check if P and Q are connected. Basically, we want to find if P and Q have the same delegate in the disjoint data structure PQ. So that's about it for this path. Then we just look at another query and move forward. So overall, we have achieved that we only look at the edge list once and only once for all the queries. So after this, we exit this for loop. We are ready to return the final state of this result variable. So that's all about the solution code. I guess let's first do a special case check. Yeah, it passes a special case. Now let's do a generic case check. Oh yeah, it passes the generic case. So I guess that's all for this video and for this solution. But before we put an end, let's read several questions. First is that can we try to implement the find function with path compression in an iterative way? So this is one challenge or one question. The second is that implement the unit function by rex to check if it can accelerate the solution. And the third item is that you are encouraged to check out other videos in the playlist to look at other use cases and check the subtle differences in implementations of the disjoint set data structure. So the principle is that we do implementations tailored to a specific problem. So that way, actually, it can demonstrate the power of disjoint set data structure. With that said, I guess we finished the video. Thank you very much.